ma'am is with us. So I humbly seek her permission to begin the event.
Yes, please do.
Thank you so much, ma'am. Very good afternoon to Professor J.D. Ahi, ma'am, Reverend Dean, sir, respected HOD, sir, eminent speakers of the day, and all dear participants. It's our proud privilege that we all are part of this webinar today. Now we are going to start the webinar with the Saraswati Vandana. Dr. Sir Harisingh Gour is not only a name for us, but an inspiration for all of us. So with his remembrance, we are going towards this webinar. Department of Physics, School of Mathematical and Physical Sciences, Dr. Harisingh Gour, Vishwavidyalaya, Sagar, Madhya Pradesh, proudly present a national webinar on the topic Metal Oxide Nanomaterials for Sensing Applications, Some Experimental Results. On behalf of the Department of Physics, I, Sherry Nasir, extend a hearty welcome to one and all. How lucky we are that we all are here and our happiness gets doubled, it being National Science Day today. How can we forget the contribution of Dr. C.V. Raman sir in the field of science, particularly in the field of physics? To begin this webinar, I would humbly request Professor Ranveer Kumar sir, Head of the Department of Physics, for his welcome and inaugural speech. Over to Professor Ranveer Kumar sir.
Hello, sir. हेलो
Yes, sir. We can.
सर मेरा ये वीडियो ऑन नहीं हो रहा, मैं मोबाइल से जुड़ रहा हूँ.
ठीक ठीक कोई प्रॉब्लम नहीं. Yes, Professor Ranveer, your address, please. आप अनम्यूट होइए, अनम्यूट. Yeah.
Okay, sir. First of all, on behalf of Department of Physics, Dr. Harisingh or Vishwavidyalaya Sagar, I welcome all of you, those who are present in the national webinar on metal oxides, nanomaterials for sensing applications, experimental results. Firstly, I heartily welcome to our Honorable Vice Chancellor, Madam, Professor Nilima Gupta, for always being inspiring us. I welcome Professor JDI, Madam, the nominee for the Vice Chancellor, as she is sparing her valuable time for this webinar. Your presence, Madam, always get great inspiration to us. I welcome our eminent guest speaker, Professor N.K. Pandey sir, from the Department of Physics, the Lucknow University of Lucknow, for kindly accepting our invitation and gracing us in this webinar. I also welcome Professor Ashish Verma, the convener, the Dean of School of Physical and Mathematical Science, for taking for hosting this webinar on this special day. I welcome all the participants, faculty members, scholars, and scientists and students for attending this webinar. I am sure all these participants will be benefited by listening the lecture of Professor N.K. Pandey sir. I welcome to the technical committee member for all their technical supports. As today is the National Science Day, and the department feels very proud for organizing this webinar on this occasion. The main objective of the National Science Day is to bring awareness to people about the importance of science in our daily life and to encourage people by popularizing science and technology. We celebrate the National Science Day on 20th February to remember the Raman effect discovery by Sir C.V. Raman, who won the Nobel Prize in the physics in year 1930. Sir Chandrasekhar Venkat Raman was born in 7th November 1888 at Trichilapalli in Tamil Nadu. He graduated in 1904 and post-graduation in 1907 in the University of Madras. He started his research in Calcutta in the Indian Association of Cultivation of Science. 28 February 1928, the Raman led an experiment on scattering of light when he discovered what now is called Raman effect. Raman effect explains the effect on the scattering of light when passes through the different material. It is a phenomenon of spectroscopy, change in the wavelength of light that occurs when the light beam is deflected by the molecule when a beam of light transfers a dust-free transparent sample of chemical compound. A small fraction of light emerges in the direction other than the incident beam. Most of the scattered light is of unchanged wavelength. A small part, however, has the wavelength different from that of the incident light. Its present is the result of the Raman effect. I'll not go in the detail of that Raman effect, but I will say that in our department today, on this day, we have a micro Raman spectrometer on which this complete Raman is there. And today from the Vidyalaya 4, the many students have visited, they are present in the department, they are visiting in this day. And that one of the quotation I want to quote that C.V. Raman has quoted, in the history of science, we often find that the study of some natural phenomena has been the starting point of the development of the new branch of knowledge. This is very important, that the natural phenomena that we are occurring in the nature, and that gives the technology. As we know, there are the 5 natural sense, that is the sense, sight is there, taste, smell, feel, and hearing. These are the 5 natural senses, and the evolution equipped some animals with these extra senses millions of years before the human evolution. For example, we have the echolocation. We have the family of marine mammals, that is the whale, dolphins are there. They can emit high frequency sound pulse and they can detect the by the echo produced by the sound. And the whales and the elephants are there. Those we can hear the sound from the very long distance. And we have the IR and UV vision also. Some snakes are there, that is rattlesnake and pit viper snakes are there. They in the night they employ the IR sensor organs, that is the infrared sensor organs are there to detect and hunt the warm-blooded prey. And similarly, we have the electrical science is there. We have the electric fish or the species of ray fish is there. They have modified that muscles, cell muscles that produce the electric charge through them and they can kill that prey. Similarly, we have the magnetic sensors also, that the behavior studies that reveals that the animals like honeybee, shark, and sea turtles are there. Immigration birds are there. They have the magnetic sensors so that they can go to their place from there where they are coming. Similarly, the smell sensors in the beer is very strong. They can sense up to 200 miles. Similarly, dogs have. They can sense the drugs, various type of drugs they have, and the cancer cells also. Similarly, in the human being, or we call the touch is the feeling. So the fingertips is one of the very good example of this one sensor. Similarly, if the fire sensors are there, there are some jewel beetles are there. They can sense up to the 100 miles, and many more are there. In the lecture, I think the sir will focus on the nano materials based sensors. Chemical sensors are there, gas sensors are there, even biosensors are there. So I will sir will focus on that. I will not take much time. And I want to tell one thing more, that our department is again organizing a international conference on the current issues in the advanced material and their applications for skills development on 8th and 10th March. That is in the online mode. If anyone can want to register on that, they can register. Once again, I thank everyone and I welcome all of you for this webinar. Thank you. Would Sherry?
Thank you so much, sir, for that great speech. Now, I humbly request Dean, School of Mathematical and Physical Sciences, Senior Professor, Department of Physics, also the convener of the event, and our mentor, Professor Ashish Verma, sir, for the introduction on the topic of the webinar.
Thank you, Sherry, and good afternoon to all. I hope my voice is audible to all. Honorable Vice Chancellor, Professor Nilima Gupta ji, though she is very busy in some very urgent work, but today we have our former Vice Chancellor of our university, Professor J.D. Ahi ma'am. Really, ma'am, your presence always boost our morale and give strength to organize such type of academic activities. And we always thankful to you. Today's speaker, our eminent speaker, Professor R.N. Pandey ji from the Department of Physics of Lucknow University. And I want to tell one thing here, that I never met Professor Pandey, but one day I go through the resume of Professor Pandey sir, and I see that the sir is working on the solid state sensors, which is my field of interest also. So definitely the day I decided that I want sir to join in a webinar, and simply I write a mail to Professor Pandey, and I wonder that within an hour, sir said, okay, I am ready. So I am really, sir, very thankful to you and your humbleness towards the physics teachers. And I hope that today we all will be very benefited with your talk. My head of the department, Professor Ranveer Kumar, who helped me a lot when I do such type of academic activities. And a few days back only, because today we are celebrating the Science Day. A few days back, we have just completed one short-term course on spectroscopy and its future application, which was organized by Dr. K.K. Day of my physics department. And that was that, and thus 28th we have this Science Day and celebrating the birth anniversary of Professor Raman. my all dear participants, all teachers participants, teachers of my department, all the research scholars, and my dear students. I hope that today we will going to listen a very important topic on the sensors and how they are prepared. And as we know that the electronics has changed towards a very new areas, and nowadays we are talking about the flexible electronics, including flexible sensors, power sources, and the conductor. They are studied eagerly due to significant advantage in terms of the reduced weight. So nowadays, this weight is going to be very reduced of the sensors, their flexibility, their durability, and their sustained multi-deformation. Deformation, I mean to say that stretching, twisting, bending, and compression, all these things are over there nowadays. And during the vigorous development of this flexible or the variable sensory system, have been studied with various sensing material, including carbon materials, biomolecules, conducting polymers, and inorganic nanomaterials to improve their sensitivity, functionality, and stability via diverse strategy. And I hope that these solid state sensors are the nanomaterial sensors basically. And all these materials, maybe metal oxide nanomaterials, are promising candidates in the diverse area of chemistry, material science, physics, and the biotechnology. I hope that today we will be all will be benefited with the lecture of Professor Narendra Kumar Pandey sir. And lastly, I would thankful to my technical team, Professor Mr. Arun Kumar Singh, Mrs. Sherry Nair, Mr. Praveen Kumar, and Ms. Swati Gurmi, who helped me, and all the technicality they are going to see. I am just giving my address to you all. So I am very much thankful to all my scholars who are working very hard for this. And once again, on behalf of my department, I welcome you all and thank you very much.
Thank you so much, sir, for those humble words. I am honored to humbly request a nominee of Honorable Vice Chancellor Dr. Harisingh Gour Vishwavidyalaya Sagar, Professor J.D. Ahi ma'am, for her blessings for the success of this webinar. Over to Professor J.D. Ahi ma'am.
Thank you, Sherry. My warm greetings to all of you this afternoon on the occasion of the inaugural session of the national webinar organized by the Department of Physics, and also on the occasion of the National Science Day with the theme Integrated Approach in Science and Technology for a Sustainable Future. We all know that science and humans achieve action in life. So today's webinar and as already mentioned by the head of pleasure to welcome the keynote speaker, Professor N.K. Pandey, into Physics, University of Lucknow. Professor Ashish Verma, Dean School of Physical and Mathematical Sciences, and also the convener of this webinar, Professor Ravi Kumar, Department of Physics. The with us on this virtual platform. I welcome you all in this inaugural session of the webinar on metal oxide nanomaterials for sensing applications. Some experimental results, which is no doubt a very relevant topic, significantly improve the quality of life in many aspects such as healthcare, environmental monitoring, and food safety. The head of the department has very nicely explained about the 5 senses, and also the dean, Professor Ashish Verma, has explained about the sensing materials. In the past few decades, nanomaterial-based sensors and biosensors have experienced rapid developments. Thus, we can say that nanomaterials have greatly boosted the biosensor field, taking advantage of their optical, catalytic, magnetic, and absorption properties. While the noble metal and carbon-based materials have been most often used, the metal oxide nanomaterials have recently emerged as a useful platform for the high stability, low cost, and versatility in chemical properties. Thus, metal oxide nanoparticles become significant components in applied nanotechnology for trace gas sensors, batteries, magnetic storage media, solar cells, catalysis, energy conversion, architecture, medicine, food, agriculture, cosmetic, textiles, antennas, including microstrip and patched optical lucent catalytic, magnetic, and electrical characteristics. Nanomaterials have shown great promise. However, many nanomaterials have yet to be explored in gas, chemical, and biological applications, which may include new biological sensing applications for emerging contagious diseases and cancer. I'm sure that the sessions will be based on knowledge and research to explore the nanomaterials and their applications for serving mankind. I congratulate the convener, Professor Ashish Verma, and his entire team, and wish you success of this webinar, and also appreciate your efforts. Dear participants, I wish you all the best for your future endeavors. Thank you so much.
Thank you so much, ma'am. We are really honored with those words of appreciation. Thank you so much for your valuable time and valuable words. Now, with the permission and blessings of Professor J.D. Ahi, ma'am, we move towards the technical session. And for the introduction of the eminent speaker of the day, Professor N.K. Pandey, sir, I request Mr. Praveen Kumar Latoria.
Good afternoon to all of you. Is I am audible, ma'am?
Yes. Yeah, yes.
Before you start, I have a request, please. Before you start, can I make a request to the Dean, School of Mathematical and Physical Sciences? I have my class after a short while, so please give me permission.
Please. Thank you very much.
Have my class.
For giving your blessing words.
Thank you.
Thank you very much.
Thank you so much. I thank you all the best to all of you.
Good afternoon to all the respected teachers and my dear friends. On the behalf of Department of Physics, Dr. Harisingh Gour, Vishwavidyalaya, Sagar, I welcome Professor Narendra Kumar Pandey, sir, for invited talk on metal oxide nanomaterials for sensing application, some experimental results. Professor Pandey has completed his graduation from Ranchi University. And then after, he has completed his post-graduation and PhD from Indian Institute of Technology, Delhi, IIT Delhi in 1995. Professor Pandey has completed his Professor Pandey is currently working as a full professor in Department of Physics, Lucknow, University of Lucknow. He has published more than 144 research papers in many national and international journals and conferences during his excellent academic career. He has delivered more than 45 invited talks on his research work in different institutions and in different time. Professor Pandey has also completed 2 major UGC research projects entitled Synthesis and Characterization of WO3 nanomaterials and their application for humidity and toxic gas sensing in 2008 to 2011, and then after gas and relative humidity sensing application of nano composites in 2013 to 2017. Professor Pandey is a lifetime member of many academic bodies such as the Material Research Society of India, Indian Association of Physics Teachers, Lasers and Spectroscopy Society of India, Indian National Science Congress, Bihar Branch Society Patna, Indian International Academy of Physical Sciences, India. So Professor Pandey has also got many honors and awards during his significant research work during his career. First significant research award University of Lucknow in 2017. Vigyan Gaurav Award by Smart Foundation, Lucknow in 2018, and many more. We are very fortunate that Professor Pandey is with us for invited talk on metal oxide nanomaterials for sensing application and some experimental results. So we are very pleased to welcome Professor N.K. Pandey, sir. Welcome, sir.
Thank you very much for giving such a warm welcome to me. I'm first of all thankful to Professor Ashish Verma for inviting me for this lecture, and I'm also grateful to the head of the department, Professor Ranbir, for giving me the opportunity to have an interaction with you. Whenever I go for delivering something, I do not call it a lecture, because from what I deliver, I learn more than what I give. So today also I hope that I am going to get something more. And I was requested by Professor Ashish Verma to make it student-centric. So I have customized my discourse in such a way that the fundamentals of what I'm doing are understandable to the students.
Right.
So many of the things may look trivial to the senior professors, and I hope and I request to bear with it. So, and about the actual research going on, if somebody is interested, we can have a talk later about that. But my talk will be based mainly for the students. So let us see. Actually, I started working first technical thing. Let me understand whether it is visible. Is the slide visible?
Yes, sir.
Yes, yes, sir, it is visible.
One more thing. Is the slide changing?
Yes, sir, it is.
Changing?
It is changing, sir.
Okay, thank you very much. So technically we are on the right point to start this. And my topic for today's discourse is studies on metal oxide nanomaterials for sensing applications. So to begin with, for students, I need them to understand what we mean by a sensor, because there are three types of research journals going on: sensors and actuators, sensors and transducers, sensors. So many people get confused about what a sensor is, what a transducer is, and what an actuator is. So when we say about a sensor, my PhD work was on fiber optic sensors. So right now I am doing solid state sensors. So my publications are there in sensors and transducers. My publications may be sensors and actuators. So what do these different terminologies mean? We need to understand them first. So what is a sensor? Just now it was said by the head about our 5 sensory organs. Naturally, anything that senses is a sensor, like our 5 sensory organs. What is a sensor? A sensor is a device that detects a physical condition or measures a physical quantity and converts it into a signal which can be read by an observer or by an instrument. Because whatever we can read finally gives the result. And what it senses is something different that may be not readable, not tenable. So a sensor is a device that detects a physical condition or measures a physical quantity and converts it into a signal which can be read by an observer or by an instrument. For example, a mercury in a glass thermometer converts the measured temperature into expansion and contraction of a liquid, which can be read on a calibrated glass tube. A thermocouple converts temperature to an output voltage, which can be read by a voltmeter, right? And the resolution of a sensor is the smallest change it can detect in the quantity that it is measuring. So maybe there is some quantity which cannot be measured, and by sensor we have to convert that unmeasurable quantity into a measurable quantity to sense that. And yes, ideal sensors are normally designated to be linear or linear to some simple mathematical functions of measurement, typically logarithmic. You see, earlier it was an earlier trend to develop a sensor which had linear relationship. But now, with the development and the complexity of the electronic instrumentation, even if the relationship is not linear, this electronics can turn those non-linear outputs into the linear ones, and we can still have a very good sensor. So linearity is no more a condition a priori, a precondition for having a good sensor. So this is about the sensor. What is an actuator? For example, valves or switches, they are actuators. So actuators are devices such as valves and switches that perform actions such as tuning things, turning things on or off, or making adjustments in the operational system. So one thing is sensing and the other is actuating, that is turning things on and off and making adjustment in the operational system. Now, these sensors and actuators are nowadays integrated. Companies now are integrating sensors and actuators to create a closed loop operational systems between some remote locations such as retail store, distribution center, etc. So we have the sensor that converts an unmeasurable quantity into a measurable quantity and then measures it, and actuators that may turn on and off like valves and switches, the sensors. The third is the transducer. The word sensor and transducer both are widely used in the description of measurement system. Now, the word sensor is popular in USA, whereas the latter has been used in Europe for many years. What is a sensor? The word sensor is derived from Latin, meaning to perceive, and transducer is from transducer, meaning to lead across. A dictionary's definition of sensor is a device that detects a change in physical stimulus and turns it into a signal which can be measured or recorded. A corresponding definition of transducer is a device that transfers power from one system to another in the same or in different form, right? So what we can say, a sensible distinction is to use sensor for sensing element, and transducer for the sensing element plus circuitry that is associated with this. So all transducers would thus contain a sensor, and most sensor would also be transducer. So we have three terms: sensors, actuators, valves and switches, and transducers. So this distinction should clearly be board if you are going to work in the area of sensors. Now, in the work that we have in the metal oxides that we are doing, the most important force that is operating in these, whether in the chemical sensors, even in biosensors, are weak van der Waals forces, not the large forces, the strong forces. They're weak van der Waals forces that bind the molecules together. They are operating, and to understand, because whenever you develop a sensor, whenever you work on a sensor, whenever you design something, it is meaningless if you do not give a background knowledge of what you have developed, because it is the knowledge that you create that will pass on from one to the other, and they will know about what you have developed. So here in this case, it is the van der Waals force that are operating in these kinds of sensors. And what is the van der Waals force? That is the sum of attractive or repulsive forces between molecules other than those due to covalent bond, not covalent bonds or electrostatic interaction of ions. They are very weak forces. They are relatively weak compared to normal chemical bonds, but certainly they play a fundamental role in the fields as diverse as supramolecular chemistry, structural biology, polymer science, nanotechnology, surface science, and condensed matter physics. So this force you need to study in quite detail, in quite deep, so that you can understand the mechanism of sensing mechanism if you want. Now, after this, let me come back to what I am going to detail about what we are doing here. That is humidity and gas sensing. Now, you must be aware why we need a humidity sensor. Very simply spoken, in the industries today, humidity is one of the worst things that industry has to manage, because a higher level of humidity may damage the whole, you can say, the very sophisticated instrumentation of the industry. In the laboratories that you work, there also a high level of humidity can damage your instruments. The food that we take, the packaging of those foods are to be done in a very controlled humidity. Similarly, about the gas, toxic gases, the sensing of toxic gases is very, very important. When we are going in the mines, what is the level of toxic gases over there, so that you can take a preventive measure before entering into that. If there is a gas leak somewhere, what is the level of gas leak, how much it can damage to the human being? These are all important factors. So, in the sustainable development that we are thinking about, we need to monitor the environment we are working. And for monitoring the environment and having a safety standard for the human being, we need a time monitoring device to control humidity and gases. And for that, for time monitoring devices, you need to sense them before the danger comes up. So that is about what is the role of humidity and gas sensor in our life. They're very, very important. But one more thing. There are a large number of humidity sensors being produced all over the world. Large number of gas sensors are being produced all over the world. So what is the most important factor? The most important factor is the cost. If you're making a very good sensor and it is costing $1,000, and another one is making slightly compromised one, but if that company is able to sell that for 20 rupees, believe me, that is going to sell like hotcakes. So the cost is much more important factor for the sensors, because sensors are produced in mass scale, because they are needed at mass scale in various places. So cost is very, very important, other than the sensitivity. These factors we will discuss slightly later. Now, generally, the metal oxides that we talk about are porous in nature. So what exactly happens? That the resistance of the porous metal oxide that changes in different environments that you expose it to. For example, it absorbs water, it may absorb gases, and its resistance will change. You monitor the change and calibrate the humidity or the gas level, concentration of gas level, in terms of the change in resistance. Secondly, if you are working with a pure metal, the results are different. And doping is something like a buzzword today in the scientific world. Doped metal oxides exhibit different types of morphologies, various properties, and have many applications. Doping has significant impact on electrical, physical, chemical, optical, and other properties of the metal oxides. Right? In the humidity sensing applications, doping improvises the sensitivity, reproducibility, response, and recovery times. It also reduces the aging and hysteresis behavior of the metal oxides. So doping has a very, very important role to play. And therefore, large number of metal oxides have been examined for sensing applications, along with the doping of the noble metals in them. So doping is very, very important, that we will see later also. Now, one thing the students need to understand, and even sometimes we also get confused, and there is a difference in the words adsorption and absorption. So these metal oxides that we use for the sensing applications of gases and humidity, here the phenomenon of adsorption is used, not the absorption. So we have to have a distinction between adsorption and absorption. This adsorption is the adhesion of atoms, ions, biomolecules, or molecules of gas, liquid, or dissolved solids to a surface. Mind it. So this is adhesion of atoms to the surface or molecules, etc. to the surface. Mind it, this is not absorption in which these molecules permeate through the surface and get into the volume of the body. So this adsorption is sticking to the surface, and therefore here it is the role of the van der Waals forces that comes into play in the adhesion of these atoms, ions, biomolecules or molecules to the surface. What happens? This process creates a film of the adsorbent. On the surface of the adsorbent, it differs from absorption in which fluid permeates or is dissolved by a liquid or solid. Adsorption, the binding of molecules or particles to a surface, must be distinguished from absorption, which means the filling of pores in a solid. Molecules undergoing absorption are taken up by the volume, not by the surface. A more general term is adsorption, which covers absorption, adsorption, and ion exchange. So adsorption are of two types, and both types are quite often used words in the you can say gas and humidity sensing applications. Physisorption, it is a physical adsorption. It is the process in which the electronic structure of the atoms or molecules is not perturbed. The electronic structure is not disturbed. Chemisorption is a subclass of adsorption driven by chemical reaction occurring at the exposed surface. Because of this chemical reaction, new chemical species will be generated at the adsorbent surface. The strong interaction between the adsorbate and the substrate surface creates new types of electronic bonds. They may be ionic, they may be covalent, depending on the reactive chemical species. Now you can understand physisorption is just sticking onto the surface, and therefore the energy involved there is very, very small. But in chemisorption, because there is a chemical reaction taking place, so the energy involved here will be larger. For example, I'm showing here a distinction between the physisorption and chemisorption. Physisorption is a general phenomenon and occurs in any solid, fluid, or gas system. Chemisorption is characterized by chemical specificity. Perturbation of the electronic states of adsorbent and adsorbate is not there, it's minimal, but change in electronic states may be detectable by suitable physical means. Typical binding energies of physisorption is about 10 to 100 millivolt electron volt, whereas for chemisorption, where chemical reactions take place, the binding energy is generally 1 to 10 electron volt. And mind it, the chemisorption has a single layer, whereas physisorption has multiple layers, one over the other. Now, let us understand, there are large number of definitions of humidity. So I will be specific to one such definition, which I'll be using during this discourse. Humidity is the water vapor content present in the air. Humidity sensor detects the amount of water vapor concentration of a pure gas or mixture of gases such as air. Relative humidity that we have been measuring here, the amount of water vapor in the air at any given time is usually less than the required to saturate the air. The relative humidity is the percent of saturation humidity. Relative humidity is the amount of moisture in air compared to what the air can hold at that temperature, that is saturation. And we are using this relative percentage humidity, actual vapor density by saturation vapor density multiplied by 100. Now, the most important factor for any sensor, humidity sensor, gas sensor, or whatever kind of sensors that we have, what are the parameters that we have to look for and therefore improve in them? One is high reliability and long service life. Because if the sensor is not giving you the reliable result, accident will be a common case. Naturally, it must have a long service life. Just one cycle of operation must not damage the sensor. Low parameter dependence on temperature. India is a country where temperature difference from one region to the other is vast. At one place, if we have temperature in the sub-zero, and then in other places, it may be 40 degrees, 45 degrees centigrade. So naturally, our sensor must not depend on the temperature. It should be by and large independent of temperature. Of the gas molecules or the increase of the humidity level, naturally presence of other gases may affect it. So selectivity, that it is able to sense one such particular gas or only the humidity, is of paramount importance. Parameter stability in media where various corrosive gases are present. Now, wide operating range should be there. For example, if it is humidity, now mind it, there is a difference. What I mean over here, that if you are preparing a sensor, that, for example, a humidity sensor, that humidity sensor may have a very good sensitivity in initial, let us say 10 to 30% relative humidity, but may not be very successful or may not have high sensitivity in, let us say, 50 to 90% relative humidity. But it doesn't mean that it is not usable. We have the industries that need humidity control in 10 to 30, 40% relative humidity because they operate in that range only. So they do not need any sensor that is very high, that is having high sensitivity in, let us say, 60 to 90% relative humidity. But there can be other industries which are operating where the relative humidity is above 60%. So naturally, the fabrication or manufacturing of the sensitivity has to be industry specific. That is, if one industry needs humidity control in 10 to 50% relative humidity, it should be given that. If another one needs 50 to 80% relative humidity, it should be given in that. So while developing a sensor, we have to see what kind of materials are useful to what kind of range of relative humidity. So you may not have a relative humidity sensor which is very sensitive, highly sensitive from 0 to 100%. Your sensor has to perform in a limited scope of a particular industry what is the need over there. So go for a special range and try to fabricate sensor in that range. High sensitivity is certainly, you will agree, is a very, very needed point. Short response and recovery time. That means the moment you introduce your sensor to the environment, it should be able to give you quick response. Similarly, if it has to be operated again and again, then the moment you take it out from that environment, it should be able to recover to its original status in a very small amount of time. So response and recovery times for a sensor is very, very important. Must be thermally and chemically resistant, should have low hysteresis. This is very important, low hysteresis. For example, you increase the relative humidity from 0% to, let us say, 50% relative humidity. And you have a particular curve. And when you are coming back from 50 to 0, is there some gap in the curve between the two, in the increasing cycle of relative humidity and in the decreasing cycle of relative humidity? Now, this particular thing, the hysteresis must be as low as possible for good reliability of the sensor. So we have to discover, let us say, sensing elements that are having high sensitivity, but certainly having low hysteresis as well. Must be highly technological and low cost. Should be compatible with electric circuits. We must be able to, because everything is electronics these days. So the materials should be developed in such a way that they should be compatible with electric or electronic circuits. When we are developing a sensor, its sensitivity is to be measured, and the world over literatures are giving sensitivity definition in various other terms. We are here giving sensitivity definition in some different terms, and this we started by ourselves, because earlier the sensitivity was given by different kinds of formulae. So earlier there were a lot of comments from the reviewers, and when we gave the strong logic for that, now they are accepting this definition of sensitivity, and many papers have come up with this, our definition of sensitivity. So sensitivity that we define of humidity sensor is defined as the change in the resistance of sensing element per unit change in relative humidity. For calculation of sensitivity, the humidity from 20 to 90% RHS Means the whole range is divided into equal intervals. You measure in equal intervals and take the average for all the intervals. And we use this formula for sensitivity, that is change in resistance by change in relative humidity multiplied by 100. And this formula we have used in most of our research papers. Now the next question is, why metal oxides for moisture sensing? For example, relative humidity sensing, or for that matter, gas sensing also. What are the advantages? Because I have mentioned different parameters for a good sensor. Then are those parameters being met in the metal oxides? Now you see, what we have, chemical and physical stability and mechanical strength, because metal oxides have good mechanical strength and because they have good chemical and physical stability, so certainly they are good for metal oxides. Now these metal oxides are good for moisture sensing. Now the biggest advantage of these metal oxides is that, number one, they are porous. So because they are porous, so moisture or gas molecules easily adhere or get adsorbed to these surfaces. In the voids, they get intercalated. So more so, they have grains, different kinds of grains in polycrystalline materials. Different grains and grain boundaries are there. You can see from there. These grains and grain boundaries provide voids, conduits, pipes, etc. for adsorption of these gas or humidity, gas molecules or humidity. So more is the presence of these things, more is the adsorption of the gas molecules or the humidity. You can see from here, because of the uneven structure, you get large number of voids and you get pore spaces also, where these gas molecules or water vapor get easily as adsorbed. So one may ask questions that, look, this particular material is porous, and therefore how do you talk about the mechanical strength? Because more is the porosity, so less is the strength. Now mind it, for a sensor, we are not going to perform a mechanical strength experiment, how much tensile it is, how much Young's modulus it has. No. In a very good mechanically strong material, these particular defects are not good if you are going to use it for some strong material, but they become merit for sensor applications because they can easily get adsorbed. If I remind you of something, during early 80s, when optical fibers were being developed for long distance telecommunication, those optical fibers had the problem that they were losing large electromagnetic signal whenever the optical fiber was getting bent. Whenever it was being bent, it has some loss, and that was inhibiting the telecommunication to a large distance. This problem was being gradually solved when another school of thought emerged over that. And that school gave a revolutionary sensor application of the optical fibers, because it is the bending of the optical fibers that gave the loss, and because of the bending, that the loss of the signal that was coming up, this measurement of the loss signal was being calibrated in terms of the mechanicals, the pressure sensor, the temperature sensor, you can say the refractive index. So various kinds of sensors got developed due to what was a weakness in the telecommunication property of the optical fiber. Similarly, in metal oxides, if you have the porosity, then of course the mechanical strength will come down, but they provide very good porous surface, having grains and grain boundaries, porous spaces, voids, so that the water molecules or the gas species could be easily adsorbed to these surfaces. And that is the advantage with the metal oxide for moisture sensing. So why metal oxide for moisture sensing? Because they provide you voids, they provide you pores, they are porous, they have grains, they have grain boundary surfaces. In the samples that we have used, grain size is below 100 nanometer. And the definition of, you can say, nanotechnology is that materials that are having their grains or crystallize in the range from 1 to 100 nanometer. And therefore, you must, if you are going to work on the nanomaterials, you should go somewhat to nanotechnology field, study something in the nanotechnology field, and then you will start understanding the properties of these materials at nanoscale as to how they change when the transformation is from the bulk to the nano size. And for this, I remind you, okay, that Richard Feynman had said there is plenty of room at the bottom. He was talking about nanotechnology when way back in 1959 during an American Physical Society meeting in Caltech. He described a process by which the ability to manipulate individual atoms and molecules might be developed using one set of precise tools to build and operate, means from a very miniature thing to a higher scale, to a higher scale, to a higher scale, from bottoms up approach, he described the nanotechnology field. Tokyo Science University Professor Norio Taniguchi in 74 defined nanotechnology as encompassing a multitude of rapidly emerging technologies based upon the scaling down of existing technology to the next level of precision and miniaturization. Nanotechnology mainly consists of the processing, separation, consolidation, deformation of materials by one atom or by, there are two approaches. One is bottoms up and the other is top down. That you can study in your own way. And I have a separate lecture for nanotechnology, that is a different thing. So nanotechnology in its traditional sense means building things from the bottoms up with atomic precision. As used today, the term nanotechnology usually refers to a broad collection of mostly disconnected fields. Essentially, anything sufficiently small and interesting can be called nanotechnology. Some experts insist that nanotechnology can refer to measurement or visualization at the scale of 1 to 100 nanometers. But a consensus seems to be forming around the idea that control and restructuring of matter at the nanoscale is necessary. So anything that has its grains in the range 1 to 100 nanometer should be called in the range of nanotechnology is not correct. Rather, at that scale, you should be able to control and restructure the material. At that scale, then you are in the field of nanotechnology. Just having by accidentally the materials that are having its grains in the range of 1 to 100 nanometer, that is not nanotechnology. You must be having a technology to control at that level. And this you can compare. Now, what is the size of a nanometer? For students, it is very, very good that this is the size of a tennis ball, 10 to the power of 8 from nanometer. You can see 10 to the power of 9, the difference of 10 to the power of 9 is there. From here, you can go and scale down to nanometer. You can see from here, this is water, this is glucose, this is antibiotic. That is tennis ball, a period, cancer cell, bacteria, virus, antibody, glucose, and water. So 1 nanometer, 10 to the power of minus 19. What do you mean by 1 nanometer? Typical carbon-carbon bond length